Okay, let us start our last talk for the afternoon session. And our short speaker today is Kantaro Ohmori, who is a Frontier of Science awardee this year, with a talk on generalized symmetry and its applications.
Okay, thanks for introduction, and I thank everyone involved in this award. So I got happily getting this award with on this paper, which I worked my variable collaborator Craig Cordova. So I'm talking about this, and so this session is technically titled as a particle phenomenology. So I prepare a slide for the particular phenomenologists, but the faces I recognize is more theory oriented. But anyway, I hope you enjoy. So this is a table of contents. Yeah. So the intro. So yeah, this talk is of course about symmetry, and symmetry is very powerful in theoretical physics, and starting from the atomic spectrum, and also like it was played a significant role in pinning down this standard model of particle physics and blah, and also so one keyword in the regarding symmetry is a Landau paradigm that relates the phase of your system, the physical system, to the symmetry pattern of happening in the phase. So that's very powerful paradigm. And for example, for the magnet, there is a symmetry acting on the spins, and it's broken in the ferromagnetic phase. But if you heat it up, then the symmetry restored, and then in the paramagnetic phase. So that's one example of Landau paradigm. But the symmetry in the conventional sense is not enough regarding the Landau paradigm. In other words, there are non-Landau paradigms that cannot be explained by the breaking of symmetry in the conventional sense. And one example is a quark confinement deconfinement transition, and another is more recent one is that the topological order in correspondence. For example, the fractional order. Okay, so one motivation of so generalized symmetry, of course, is a generalization of symmetry as it says, but the one motivation of doing so is to generalize the notion of symmetry so that we can describe those phases as extended or generalized or categorified Landau paradigm. Okay. So take home message. Okay, so as I said, I prepared this slide for the particular physicist. So the message is that general symmetry is in particle physics, but more broadly, that the general symmetry is everywhere. Okay, and so general symmetry can be classified in two types. There are many others by now, but mainly two types in this talk. And one is a higher form symmetry that's pioneered by the couple in in 2014. And so the example of that, most important example of that is the center symmetry in gauge theory. And more recent one, well, it's older, but in higher dimensions, more recent one is a non-invertible symmetry. And so yeah, this non-invertible symmetry was essentially known in 1+1D systems for 2 decades, 3 decades. But in higher dimensions, it's more recognized more recently. And key contribution of my awarded paper, and also like co-awarded paper by Icho, Hotot, and Shuhan, is to say that this famous and old ABG anomalous chiral symmetry in QED can be regarded as preserved but non-invertible symmetry. So, and I believe that this opens up a very many research direction, and right now the general symmetry, but the non-invertible symmetry in high dimensions is a fruitful field of research. Yep. And so that's the main part. In the last two slides, I'd like to briefly mention about my more recent work on the representation theory or higher representation theory regarding the general symmetry. Okay, so that's a take home message. And okay. Okay, so general symmetry. So yeah, so I start from very basic thing. So symmetry organizes the physics by a representation theory. And so, for example, if you think about the hydrogen atom, then there's a SO3 rotational symmetry, and then you expand your wave function in terms of spherical harmonics, of course. And there's also a so hidden symmetry, you might call it. That's a linear length vector, which also preserved by the time translation. So together with the SO3 and this quantity, it generates SO4. And this SO4 symmetry is responsible for the degeneracy you see in the spectrum of ideal hydrogen atom. And so the lesson here is, of course, first the representation theory is very powerful, and that organizes the spectrum of physics. And also, like symmetry, if you have a symmetry, then that related to the conservation law in sense. And in addition, the system can have a hidden symmetry that might not be immediate to see, and you might have to be a little bit clever to find. Okay, so that's another thing to notice. Okay, so this is quantum mechanics, and going to the QFT. Well, basically the rule is basically the same. Symmetry is related to the conservation law, but here the QFT has a locality, and so when we talk about symmetry, we also want to care about the locality. In particular, so usually we think, or almost in most cases, we consider the symmetry transformation, which sends the field at value about the field value at the point x is sent to something else, but that's a function of field value at another point. Maybe that's itself. Okay, so this is a locality preserving symmetry, and it's not phi prime is the integral, or it's not the phi prime is usually the integral of phi with some test function. Okay. And okay, so the preservation of symmetry, or the existence of symmetry, is defined as the preservation of the action under this local symmetry transformation, and the theorem tells that in this case you get charge density, and by integrating the charge density over the space, then you get the net charge. Okay? Again, so precisely because that we started from locality preserving symmetry, this charge is expressed as an integral over your space. So it's local in that sense. Okay? I'm of course talking about the global symmetry, but yeah, there's a locality. Okay, that's what I'm emphasizing. And of course, it is conserved if this is satisfied, and of course the symmetry corresponds to the conservation law. So if it's a time translation, then the corresponding law is the energy conservation. If you are talking about the phase rotation of your field, then that's some electric charge conservation. Yeah. So this is I already said, and the locality, the preservation locality in the symmetry transformation is very important. And so to generalize, we want to also care about the locality. So actually, the guiding principle of generalization is, so we shouldn't be doing random generalization, that we should be doing a useful generalization, and to do that, the locality is a guiding principle. Okay. So higher form symmetry is pioneered by a guy of the composite period. More than a decade ago, is one generalization of symmetry, and so the conventional symmetry, your charge is an integration over space. So integrating your charge density over space. Okay, but you can also contemplate the case that there's some quantity, then you integrate over some higher codimensional manifold of your space-time, and then and contemplate the case that this quantity is present. Okay, so that's the called the P form symmetry when this sigma has a codimension P in space. Okay, so the conservation law, to be precise, the conservation of such charge is defined as a topologicalness of this. In other words, if you define the sigma, if you deform the sigma continuously without crossing that other operator, then this defines that, I mean, any correlator including these operators should match under the continuous deformation. And in particular, that if you can think about the shifting this sigma in time direction, and then that should be invariant. So this Q is constant. So that's the definition. So example, there example is actually just a Gauss law you learn in the undergrad in the electromagnetism. So yeah, so just if you have a charge and so that you in QFT you think it as a Wilson line, the heavy charge particles. So it's a Wilson line, and if you encircle that charge with a Gaussian surface, then you measure the charge emitted from the flux, electric flux emitted from this charged particle, and integrating over this Gaussian surface, and you measure the electric charge. Okay, so that's very usual familiar story, but that's now in this definition, it's one form symmetry. So it's a new type of symmetry, and in this case, the law is of course the electric flux. Okay, the electric flux you're integrating over the codimension one surface within the space. Okay, and there's a corresponding transformation law in this case that is just shifting your gauge field, U1 gauge field by a flux condition. That's a transformation law, and you can make regard this in terms of this one form symmetry, that you can regard this photon as a non-Gaussian mode on this spontaneous symmetry breaking of the electric one form symmetry. Okay, this is all in this original paper. Another important example is a discrete version of that, just discrete version of that. So if you think about the SUN gauge theory, then there's no U1 charge that you can define, but actually so SUN have a center Zn, and you can define this Gaussian surface type operator for the center. Okay, so there is Zn one form symmetry, so-called Zn electric one form symmetry, and then so the lower is or yeah, I mean maybe more than lower, but what everyone believes is that the deconfinement corresponds to the one form Zn one form symmetry breaking of this electric. Okay, and this is the extended Landau paradigm, and yeah, I'd like to comment more on this at the end of the talk. Okay. Okay, then non-invertible symmetry. So non-invertible symmetry is another way of generalizing The symmetry, of course, we can do the both and we can think about non-invertible higher symmetry, but here just non-invertible symmetry. And so to do that, first before generalizing, I just want to introduce the exponentiated charge operator, just exponentiate by with the angle. Okay, and then the non-invertible symmetry is kind of generalization of this operator into this. Okay, so here we allow so define a sigma and well, for the zero form case, the sigma is entire space. Anyway, so here for non-invertibility, we allow to introduce additional field, additional to the bulk field you have. So you have bulk field, but you be allowed to put additional field only on this defining surface. Okay, then you integrate them over that field and with some action. And this action, of course, couples this additional field to the bulk field, otherwise decoupled. Okay, that's the general form. Of course, you don't do the random row. There has to be a very stringent constraint on this of this kind form. Okay. Anyway, so you can one way of thinking of this A is to so this is auxiliary field on sigma, but you can also think so in the quantum information theoretic term you can call it ancilla on sigma. And so yeah, there's a very nice illustration in the interpretation of non-invertible symmetry proposed in Sahan, and you so following his word, I can describe this non-invertible symmetry transformation as the following way. So we started from some system with the phi is my bulk field, and then we then we introduce some ancilla qubit. Okay, so they prepared and this state of this ancilla is prepared in nice way. Okay, then they interact. So this ancilla and we let this ancilla qubit and the bulk field to interact in or doing a unitary, if you like, if you want to be a quantum information theorist. They're doing unitary, particular unitary, and then at the last stage, we remove this ancilla, and that means the measurement. So you measure this in the particular direction, and then so that's the general way of implementing this kind of transformation. Okay, and so this is a kind of way more general thing you can come up with than doing unitary on each qubit, but it's still okay. So I recommend this is still local. So this is just a local operation, and so then and of course we don't think about the random row, but we want this is still be conserved, and that means that we still demand that this operator is invariant under the continuous deformation of sigma. Yeah, and we call it non-invertible because so in this Sahan's presentation that at the end of the day we are doing measurement that clearly breaks the invertibility. So this is a projection, you are doing projection, and projection is not invertible. So yeah, so the general framework of non-invertible symmetry. Any question until this point? Yeah, I'm giving this. Yeah. Okay, so in the Higgs phase, this one-hole symmetry is not broken. That is. Yeah, thanks for the question. Okay. Oh, yeah. And the sorry, I stopped the wrong part. But okay, so another comment is that this non-inverted symmetry is interesting in the quantum information theoretic sense because it can alter the microscopic entanglement structure as opposed to the conventional symmetry. And for that reason that it plays important role in topological order. But yeah, here in this talk, I'd like to rather talk about this more QFT particle physics type example. That's the next thing to talk about. Okay, so this is about so this is the main part about this paper, and I worked with my collaborator Clay Cordova at Chicago University. Yeah. So this is about the AB generalized symmetry in QED. So and Bell-Jacques famously pointed out that the chiral symmetry. So this J is chiral symmetry, and the chiral symmetry current. And if you compute the divergence of chiral symmetry current in quantum mechanically, then there's it's non-zero and the proportional to the field strength squared with epsilon. Okay, so usually it's said that this symmetry is quantumly broken, but the key claim of ours is that we can save the symmetry, but we have to give up the invertibility of the symmetry. So if you give up the invertibility of the symmetry, then we can save the symmetry. So let's try to save it. So one obvious thing to try is to modify this current by Chern-Simons term. Okay, so to cancel this part. But obviously, this current is not gauge invariant. So this is not enough. Next thing is to integrate over the sigma is just space. Right? So integrate over space, and the so then this thing is invariant under the local gauge transformation, but still not gauge invariant under the large gauge transformation. Okay. And so slightly non-trivial thing to do non-trivial next step, but natural in the recent context of generalized symmetry is to exponentiate this charge. Okay, so exponentiating, just putting on the shoulder of E, putting alpha, but then we take alpha to be the 2 pi times the rational number. Okay, so this is maybe this is the most non-trivial point. And okay, so we arrive to this operator. Okay, this operator is not good enough. Still, like this is fractional and not invariant under the gauge transformation, large gauge transformation. But we've seen so humankind have seen this kind of action before, and this is exactly the response function for the fractional Hall effect. Okay, for the filling fraction P over Q. Okay, so this is like we are trying to describe fractional Hall effect on this virtual surface sigma, and we know how to resolve this non-gauge invariance, and it's resolved because so in the fractional Hall effect context that it's resolved by noticing that it's actually a TQFT. And here, like as a technical operation that we integrating in a new field on living on sigma. By the way, I'm taking P to be 1 for the simplicity. So in that case, okay. So anyway, we pick A. We put A. So the additional field on sigma, and then write this action. And this action now is well quantized. So Q is integer, and this is well quantized chance amount action, the mixed chance amount action, and the so the small a is the auxiliary field on sigma, and capital A is reminds you that the electromagnetic U1 field. Okay, and you can easily check that when A is infinitesimal, integrating small a, then you get back this. So and this is perfectly gauging. Okay, so this is the construction. Okay, and the important comment to make here is that this trick, the last part, is not available for the non-abelian gauge group. So for non-abelian gauge group, this I mean, the anomaly takes the same form up to this trace, but because you have trace, this is not the square or something in any way. So you cannot take this as square. This is essentially taking a square root. Okay, and you can take the square root. So it's yeah. So you cannot apply the last trick to the non-abelian gauge group, and physically we shouldn't be able to do that because instanton. So for non-abelian gauge group, there's local instanton that physically breaks the symmetry. And therefore, really, the chiral symmetry is broken locally, I mean, by a local effect. So there shouldn't be any way to save that symmetry. So yeah, so that's just consistent. Yeah, and yes. Okay. Okay. Yeah. So yes. So either if you put the box or you put the periodic boundary condition, then you do have you do have instanton, but that's a global effect, and in a sense that kind of global effect can be captured by not this TKFT degrees of freedom on sigma. So we can So in it we can think about I did write a paper about this non-relative symmetry in the case of non-trivial topology, and then so in that context, this TKFT part plays interesting. Thanks for the question. Yeah, but no abelian case, the instanton is completely localized solution, so that's the difference. Okay. Okay, another comment is that this non-relative symmetry operator, you have a chance theory on sigma, and that couples to the bulk field, which is electromagnetic field, and this is magnetic flux. So in a sense that in an appropriate sense, this operator is a mixture of naive chiral symmetry and this U1 magnetic symmetry. So U1 magnetic symmetry is just a magnetic version of Gauss' law, but yeah, and from this expression or this formal understanding, that we can say that if you have a monopole, then this chiral symmetry is broken. This monopole supports this non-trivial magnetic flux and explicitly breaks this symmetry. And that's just another way of saying the monopole catalysis by monopole catalysis of chiral symmetry breaking or product of decay of chiral block. And so a bit more concretely, so if we consider the embedding of our U1 electromagnetism into the non-abelian gauge group at some scale, UV scale. Okay, so this, let's assume that this, as opposed to the standard model, that this is embedded into the non-abelian, simple non-abelian gauge group, maybe GATT. And then you have a dynamical monopole. For example, in the GATT. And so there's a monopole, quantum mechanically makes a loop. Okay, so there's a loop correction from this monopole, and that breaks the chiral symmetry for the same reason. And this effect, however, is exponentially suppressed by the monopole Wilson line as a monopole world line action, which is roughly estimated by this monopole mass times the monopole core radius. And on the other hand, as I said, that in non-abelian gauge group there's an instanton. So in the UV above the scale you have instanton, and this explicitly breaks this locally explicitly breaks this chiral symmetry. Okay, and this is a yeah, and the instanton effect comes with this factor as an instanton factor, and the interesting thing to notice is that if you compare this factor and that factor, actually they're roughly the same. So this is the monopole mass is the scale over G Yang-mills, and monopole core radius roughly the 1 over scale times G Yang-mills. So this is actually 1 over G squared. Okay, so we want to say that these two effects are actually the same. Okay, so to be more precise, and this is already before this kind of like monopole loop, the correspondence between monopole loop and the instanton in the UV is pointed out by this paper. And to be more precise, that we have to sum over the electric charge. So we have to think about the dione loops and sum over the electric charge with a fixed magnetic charge, and that corresponds to the UV instanton effect. So that's so they check this equality to the BPS case, and also like more recent paper constructed bringing the dione configuration and compute the instanton on the background and precisely found this correspondence. And so so in this paper, the paper that we also tried to take advantage of this fact that chiral symmetry can be broken by monopole loop, which is equals to the instanton effect. And so if you assume that this even at the UV scale, this chiral symmetry is perturbatively protected for maybe there's no happens to be emergent symmetry, that there's no relevant operator that breaks the chiral symmetry. And then but anyway, that in the UV, this instanton / monopole effect anyway breaks this chiral symmetry, and in this way we can get this kind of suppression. So naively, if this symmetry is broken at scale, then you get this factor. That's what you learn in any EFT course. But then this is comes from this monopole / instanton effect comes from, of course, instanton effect. Okay, so this is, of course, just I'm just saying that the fifth vertex can generate this kind of operator, but here the point is that we can by analyzing the chiral symmetry in the IR and UV model, that we can systematically predict that the Fitch operator is generated in this via the fifth vertex. Okay, so there's a systematic way of predicting this small generation of the higher dimension operator in the IR. And so in this paper we applied this kind of philosophy to cook up some model that generates this neutrino mass of some monopole dione loop. and by this kind of Feynman diagram. And yeah, so that's just one application. Okay, so any question until this point? Yes. Okay, so we cook up two models. One is Dirac and one is Majorana. So in this just yeah, this is just a mechanism that you can hire and yeah, we could find the both scenario. Oh yeah, okay, yeah. So for the Majorana case, of course, yeah, we add the Majorana fermion and then yes, yeah. So in the two cases, a slightly different chiral symmetry are considered. Yeah, and so that's okay. And then I'd like to talk about the representation theory. And okay, so as I emphasized at the start of the talk, that representation theory is why symmetry is powerful. The part of why symmetry is powerful. And here, recently, I've been thinking about working on this representation theory that is suitable to describe excitations. So another thing to describe is the operators in QFT, but here I'd like to think about the excitations, such as charged gauge charged particles or other solitons. And okay, and the crucial thing to notice when you're thinking about the excitations is that the set of the set of excitations drastically depends on the phase. If you're in a different phase, then the excitations are completely different. Okay, so then correspondingly, the representation theory or the representation category or the algebra you should think about depends on the phase. Okay, so the set of possible representations are completely different depending on your phase. Okay, and so Hayekon, yeah, and for Hayekon symmetry, also like to describe these excitations related to Hayekon symmetry that actually strings the vortex. Vortex is the higher dimensional object. Then we have to hire the representation. Okay, and for non-negative symmetry, there's also a very interesting thing to say, but let me skip that for the time constraint. Okay, so in the paper with Fingariano and Andrea Gruletto, we consider specifically consider this kind of setup or SUN gauge theory or 3+1D SUN gauge theory with some scalar clock, single scalar clock, and added adjoint scale Higgs, and thinking about the zero temperature. And so when this adjoint Higgs mass is actually Higgs and just decoupled with the positive mass squared, then it's supposed to be in the confined phase. And so we can I don't have any time to explain the detail, but we build up the mathematical some formalism. You just conjecture the mathematical formula that computes the higher category representation, the higher representation category. That's some higher category, some mathematical gadget, and for each of phases in this theory. Okay, and we analyzed and we found that this mathematical gadget contains the constituent that the higher representation corresponding to the confining strings and also variance. Okay, so that's and in the deconfined phase we also do representation theory, and we found that this representation theory correctly contains the color vortex that's going around and there's a center of gauge field, and this one includes the clocks. Okay, so the point here is that in this particular setup, just not the theorem, in this just a particular one example, that the confining string in the phase that there is a confining string, then there's no quark. And in the phase that there's no confining string, then there can be a quark. And of course, this is physically intuitively expected. Because if there's a confining string, the literally says that it confines quark by binding quarks. But there's the universal mathematical gadget we can play with, and that reproduces this. So that was I was kind of satisfied with this trivial result. Yeah. So then I maybe I slightly faster than I thought. I finish. So the general symmetry is prevalent in particle physics, or more generally, I think many places in theoretical physics. And so one is the half-mode symmetry, and whose important example is the center symmetry in gauge theory. And our contribution was to find the non-invertible symmetry in QED, and that's just the ABG anomalous chiral symmetry interpreted as a non-invertible symmetry. Okay, so that's the ABG anomalous chiral symmetry can be saved as a non-invertible symmetry in the abelian gauge theory. Okay, and yeah, that's what I talked about the representation theory symmetry. Yeah, okay. So prospects of hope is to get new perspectives and techniques and ideas from general symmetry in say in this session, say in particle physics. And yeah, so we obviously already tried. Yeah, as I said, that we with Clay and the Seth and Sangu, we tried to apply it to the neutrino mass generation, and so I was not included, but my collaborators on the paper also worked on the strong CP problem. And so this is and there's also another paper. This is not particularly motivated by this non-invertible symmetry, but very closely related to the idea that trying to addressing the strong CP. So those other hierarchy problems, maybe non-invertible symmetry, this particular non-invertible symmetry might be useful. And of course, one can be more ambitious to think about electroweak hierarchy or cosmological constant, or I mean, one should be ambitious, and I have no idea, but yeah, that's just comment. Yeah, and yeah, for the higher representation theory, that the so far, yeah, I've just checked this. I only have a sanity check that it works in the way it's supposed to, but yeah, but this is the point is that this representation theory is systematic and supposed to give you classify the objects or excitations of any kind of extended, including extended excitations in the more complicated theory, maybe. So you might be interested in that kind of computation for maybe in the early universe cosmology or like that. So that's wonderful. So I stop here, and thank you for listening.
Thank you for your talk. Some questions or comments?
Yeah, you discussed this SUN example with a joint representation. Well, I can imagine that if n is large enough, then a joint representation doesn't break completely SUN. So there are some non-abelian parts which still survive. I would expect that for this non-abelian parts, you are still defining ways how this fits what you said.
Thank you very much. So I didn't really. Okay, so this is just a representation theory, and I here, I there's no
I
yeah.
take SU5, this adjoint is 24. I break to SU3 plus 1 plus SU2.
Yeah.
Part is confined and SU2 part is confined.
Right. So the thing I can do is, So first of all, there's I didn't say anything, but the classification of gapped phases, and so far this formalism is applicable only to the gapped phase. That's one comment. And for the gapped phase, So I think when n is complex, then you can think there are various ways of partially break the central symmetry because there is a subgroup in the end. So in large n, of course, you can think n being a very composite. So in that situation, we can talk about more intermediate kind of phase and try to do the representation. Very important.
Maybe one more question.
Yes.
Suppose I know nothing about non-invertible symmetries.
Yeah.
So this type of formalism, it does what? It presents a new view of the old phenomena, or you can discover something which cannot be discovered by other methods.
So yes, so that's I think very important question, and kind of yes. So this is just a modern kind of, or maybe just a pedantic. If you're critical, then you can say that this is just a pedantic restatement of very old fact. And but I think the point is okay. So this is more technical, but more systematic. So eventually, so far, what I've said is like almost everything can be done without knowing symmetry. But I think eventually the being systematic becomes more like advantageous, and so that's In other words, this kind of like only recently we start to understand this mathematical structure of general symmetry. And on the other hand, for the usual group, the Wigner applied this group theory to quantum mechanics in a century ago. So there is a like century of disadvantage in my head. So it will take some time to. So there's a backlog of phenomena to explain. That's already known phenomena to explain in terms of this kind of new formalism, and it's taking a while to clearing up this backlog. But even I hope that eventually we are starting to produce more and more new results. So that's my hope.
Other questions? So if not, let's thank our speaker again.
Thank you very much.
And that's all talks for today. So